Hey everybody, I had some weird connection issues with my microphone earlier. I got them fixed though. Should have class on the 25th. Hopefully, there won't be any other issues besides what we already had. So, I'm here to give a broad overview of the power plant that we're going to be doing thermo with in Excel. Now, there's going to be several assumptions that we'll end up making, um, and this is going to get y'all familiar with the way that uh, thermo works so that later on you can use it on your tests, but more importantly, you'll have a basic understanding of it whenever it comes time to start using like Aspen and um, and other chemical engineering concepts. So what you're going to be looking at right now is this power plant. So we got a Rankine cycle right here, and it's hooked up to via the a heat exchanger to a Brayton cycle. So we have a Rankine cycle and a Brayton cycle. Brayton cycle is basically a jet engine. It's similar to how those work. So these things are really loud. That's the gist. Um, for the Rankine cycle, we're going to have steam that comes around on the inside of this thing. So at stage 5, 6, 7, 8, and 9, we all have steam there. And it's going around in this circle where the pump is compressing it, getting it to a really high pressure, and then we're adding heat to it on at both of these heat exchangers. And so what that does, it gets it up to a high pressure and temperature, so that we can then later in this turbine drop it down and drop the temperature so that we can draw work off of it. That's how the gist of how that works because of the energy balance. The work is directly correlated to temperature and pressure. Yes. Um, and then later on we cool down even more the right here we cool down the steam even more so that we can pump it through the pump again and just keep sending it back around and around and around and around this cycle. All right. And the same idea happens inside of this jet engine, except it's not in a circle. What happens is that you compress air, and then you um, heat it up, and then you draw more work off of it after you've heated it up. And just because you've heated it up means that you should be able to draw more work off of it than is required by the compressor. And so, in total, you should, if you do your math right, have a net work that is positive and thus a power plant. So, what are all these assumptions that you're going to have to make? Because we got cooling water here, we're going to have fuel, we're going to have air, and um, one thing I would like to mention before we even start is that the pressure of the air at right here is going to be the same as the fuel. So I'm just going to go ahead and write right now that P13 is equal to P14, just because if they weren't at the same pressures, then we'd have a backflow and we'd therefore have an outlet of air, so that would be decompressing. It needs to be, the fuel needs to be at the pressure of that compressed air so that it doesn't leak. Um, what else? What else? This stream is heat right here. After we draw more work off of it, we're using that hot gas to help heat up the steam again so that we can draw even more work. If this weren't here, if this weren't there, we wouldn't be able to draw as much work off the turbine over here because it's just not as hot as it could be. It could be hotter, so why not make it so? So we do. Now we're going to assume that it's ideal gas. We're also going to assume, don't write it down yet, if you haven't. Nope. I feel like this would be a good spot to put this. We're also going to say that the CP is non-constant. So we're going to use the yellow sheets to find our CPs. using the A, B, C, and D values. Now, we're also going to assume that the extent of the reaction, so however that reaction that's occurring both here, sorry, both here and right here, those extents of the reaction is going to be 0.8. We're just going to say that it doesn't completely combust all the way because it's, I guess, too fast for it to continue to react. For all the compressors, turbines, and pumps, we're going to assume that they're adiabatic and that the isotropic efficiency is 0.92. Dr. Griffith mentioned something about that being not as efficient as it could be, and I am curious what he meant by that. I don't know exactly what he meant by that, but I am curious to know more about what he means. Of having both the turbine and the compressor, having those at the same isentropic efficiencies. I don't know. I'm not very sure about that. But that doesn't matter. That doesn't matter about this. It's not as efficient or something like that. Now, all heat exchangers that they're having a delta P of 0. And to a start, as far as the assumptions would go for turbines and compressors and pumps, we're gonna first assume that the work is ideal, so that delta S gen is 0, but then later we'll take this assumption away. Sorry, we'll just take that assumption away and say that it is irreversible. I'll show this through the math, but then we're going to find the real work after. So we start out by saying this, step 1. So that's 1, and then 2, we say it's irreversible, and then we use the isotropic efficiency to find the real work. Okay. What else? And so like that assumes that it's reversible to start. So this is a table of just the assumptions that you'll end up needing to make. I'll post this to Moodle. You'll see it what I'm talking about. But that's what this is. A few things that I wanted to say though is right here it states 7, so that's at the turbine outlet. You can't have a quality that is, or you shouldn't have a quality that is less than or equal to 0.95. If you had a quality that's less than that, then the turbine would break necessarily. It would break sooner, I believe. You're putting liquid water. I mean, if you think about it, you have quality that's less than that. You're putting too much liquid water through that turbine, and thus causing it to rust, I suppose. I'm not quite positive. I just know that it decreases the life of a turbine, and you wouldn't want to do that. So you keep the quality above 0.95 right there. But for this one, it doesn't matter as much because you only have like a little bit of water in it as the product mix. I think it's like something like, I don't know, 20% water. You'll figure it out. You're going to need to assume that the pressure for that Brayton cycle is some sort of pressure ratio, but it needs to be high. So if I'm at atmospheric, I think a pressure ratio of 10 is good. So like something like, you'll have 147, but it doesn't matter. You could have it be 20 if you wanted to. So whatever, however low or high, as long as it's within reason. I think that having a pressure ratio somewhere between, so like what I'm saying when I say pressure ratio, P12 over P13 is equal to actually, no, P13 over P12. Something like, 10. Let's go with somewhere between 7 to 13. So, like, let's just keep it in that range. That way, um, yeah. 10 is a good one. 9 is a good one. They're all good. Doesn't matter. But nothing higher or lower than that. You don't want to draw too much work so that the equipment breaks. You can't have too high of pressures. You're going to want a really high temperature coming out at your outlet of that Brayton cycle. However, the higher you can get this, the better. Um, that'll be set to something, but I mean, as well, also you don't want it to be so high that it breaks. But as far as an idea of how much work you can draw off of the temperature, you want more. You want the higher temperature, the highest temperature you can get, so you can get the most amount of work. But that also your equipment starts to break after a while, so you don't want that to happen. I believe that is all the assumptions that you're going to need to make. Oh, dew point plus 50 degrees. I didn't mention that. So right here at state 4, you're going to cool down using the heat exchanger. You're going to cool down this product mix to dew point, to whatever its dew point is, plus 50 degrees, so that it doesn't create uh, dew. You don't want the water to condense. So that's why we're keeping it 50 degrees Fahrenheit above that, so that we make sure that the minimal amount of um, water or whatever other gases are in there that could condense do not condense. We don't want that to happen. We want that to be sent out into the atmosphere in a column so that it doesn't um, come out as liquid water and go somewhere else, or come out as a liquid and contaminate something else. Let me know if you have questions. Please email me. Feel free to email me or call me. I'm gonna put that again. So if you need to call me, call me at 337-263-4443. More than willing to answer your questions at whenever. Doesn't matter to me. And my email is this. So I hope y'all are doing well, and